So my goal today is to look at some of the operations that we did yesterday in more of a graphic form. Like we did vector addition just by drawing it. All right. What I want to do today is look at doing vector addition or subtraction or constant multiples, those kinds of things in component form. All right. So, and the nice thing is it's actually pretty intuitive if you think about it. Okay. So I have u and v, vectors u and v here, and v I just made AB and u I made CD. And if I'm going to do vector u plus v, I take the horizontal component of u, C, plus the horizontal component of v, so C plus A. And that's going to be the horizontal component of my result. All right? Then I do the vertical component of u plus the vertical component of v, and I have d plus b. That's going to be the vertical component of my result, my resultant vector. Okay? Now, I put on here also v plus u. And what do you notice about the results? Huh? It's not different, yeah, because addition, these are just numbers, right? These are just constants, A and C, B and D, B and D. So I know that addition, when I'm just adding numbers, is commutative. So we actually could now say that vector addition is also commutative. It doesn't matter if I put u plus v or v plus u. All right? And actually, if we think back to what we did yesterday, if I have this vector 4, negative 3, that's going to be something like this, right? 4, negative 3, that's u. And if I had v, which is 1, 6, that's going to be something like this. All right? Well, if I did v first, and I started at the same point, whoops, I need to do v identical, okay? So that, let's say that's v, and then I did u, guess what? I end up with the same result, okay? I end up going from here to here. So my resultant vector is the same whether I do u plus v or v plus u. Vector addition is commutative. We can see that, but let me erase these. Okay, but now we can actually see it algebraically. All right, so if I were doing a u plus v here, my vector would be 4 plus 1, negative 3 plus 6. Okay, so 5, 3. That would be it. So I know that if I were to draw this resultant vector again, this would be u plus v, not 4, v, okay, and that would be my vector 5, 3. All right, does that make sense? Pretty simple. So we can do other things with these as well, all right? And I want to start kind of putting these together. We saw yesterday that when you add vectors together, like let's say this is the vector 2, negative 6. This is v. If I want 4 of them, we saw yesterday we can just draw them one right after the other. Okay, but if I'm looking at that in component form, for v, total, I ended up going 2 to the right, 2 more to the right, 2 more to the right, and 2 more to the right. Okay? So total, I ended up doing 8 units to the right. Okay? Does that make sense? And then if I look at the vertical components, I went down 6, and then down 6 more, and down 6 more, and down 6 more. So 6, negative 6, negative 6, negative 6, negative 6. So total, I went down 24, so negative 24. And that's why we see that if we're doing a multiple of a vector, we can simply multiply the components by whatever that constant is. Alright, so 4v is just 4 times 2, 8, and 4 times negative 6, negative 24. Okay?
I missed where you got 4 from.
We just wanted to find what 4v was.
Sorry.
It's okay.
I actually didn't even see the 4. I don't know how, but I just didn't even see it.
That's okay. Alright? Now, let's think about what this does to our magnitude. Does anyone have a thought of what they think it does to the magnitude? Yeah, Anna, that's right. It multiplies it by 4. Let's actually see that happen here, okay? So if I found the magnitude of that 2, negative 6, okay, magnitude of v up above, I'd do the square root of 2 squared plus a negative 6 squared. So that's going to be 4 plus 36, right? So square root of 40. And if you simplify that, that's 2 root 10. Okay? You all know how to do that. However, what if I did the magnitude of 4v? Well, the magnitude of 4v has components 8, so 8 squared plus a negative 24 squared. Okay? Well, 8 squared is 64. 24 squared is 576, yeah. If I add those two together, I get 640. Okay, and if I reduce that, 640 is 8 times 10, right? Or I'm sorry, 64 times 10. And the square root of 64 is 8. So this is 8 root 10. Well, what's 2 root 10 times 4? Not a trick question. What's 2 root 10 times 4? 8 root 10. Okay? So look, what we end up doing here is we simply multiply by 4. When we multiply the vector by 4, we multiply the magnitude by 4. So what we could say then, to just put this together, the magnitude of c times vector v is just c times the magnitude of vector v.
But if you look to the square root of 40, would you just make it the square root of 160?
No, it would actually have to be times 16 since it's in the radical.
What?
Just don't leave it as radical 40. I mean, here's the thing, if you wanted it simplest, I mean, it'd just be 4 radical 40. You could just multiply it that way. But you should simplify your radicals. Okay. Yeah, Christiana?
No.
Okay. All right? So that's how we deal with scalar multiplication, and that's what happens with our magnitude when we do scalar multiplication. Okay? So now we can combine various operations together very easily. Okay? Here's where this is so much nicer than actually doing it graphically. If I wanted to do 2u minus 3v, okay? If I were drawing this, you know, I'd have to do, okay, 4 negative 3 is something like this. Here's my 2u, and then a minus v is negative 1, negative 6. So that's going to be like this. and I'd have to get 3 of these, and then I'd have to figure out where exactly this is. This is 2u minus 3v. Okay? U minus v, and minus v. Okay? So this vector here is the one that we're actually looking for. But we can do it very, very easily. We don't have to have a grid drawn to put it on. We don't have to do anything that complicated. All we have to do is work with the components. All right, so first of all, 2u is going to be 2 times 4 and 2 times a negative 3. So we have 8, negative 6. Then we want to subtract 3v. Well, 3v is 3 times 1 and 3 times 6. So now when we're subtracting, we simply subtract the horizontal components. 8 minus 3 is 5. And then we subtract the vertical components. Negative 6 minus 18 is a negative 24. Okay? So now I know that this vector here is the vector 5, negative 24. Okay? And that makes sense based on our drawing. Now, I didn't draw this perfectly, obviously, but it at least makes sense. I went a little bit to the right, and I went down a whole lot. Okay? So 5, negative 24. Yes?
It's in absolute value, right? The magnitude, or is that just...
It's really not absolute value. The notation is used for absolute value, and the notation is used for magnitude. Really, absolute value is kind of a special use of magnitude, okay? If you think of absolute value as your distance away from 0, like the absolute value of 5, it's really the magnitude of the distance, you know, of that vector, you could say.
Yeah, I just wanted to make sure it didn't affect it at all.
No. Now, all of your magnitudes will be positive because you're taking a square root. Okay, so this is going to be the square root of 5 squared plus a negative 24 squared. So that's the square root of 25 plus 576, which is the square root of 601, which I don't think simplifies. Okay? So, we're doing a lot of this stuff we started doing yesterday, but now with components, it's much easier. We can just deal with the numbers. We don't necessarily have to draw all the things between. Okay? So if I were graphing this vector, all I would have to do is draw the blue one, the result. I wouldn't have to draw the separate ones, okay, because I can figure out what the result will be algebraically instead. Okay. All right, so let's put a couple of the ideas we've looked at together today in order to do this one application. This is an application that shows up a decent amount, and that is when we have a direction. Let's say we have some direction vector v, and let's say v is the vector 8, negative 15. Okay? what we want to do is find a unit vector. Now here's a definition that you need to make sure you know. What is a unit vector? What's the unit circle?
I don't know the definition for it.
I know it.
Come on. Most of the people who normally answer all the questions are doing the project, so you guys are going to have to participate. There's no hiding this unit. Okay? Think. What's a unit vector?
From a circle?
Well, what was the unit circle? The unit circle was a circle that had a radius of 1. Okay? A unit vector is a vector that has a...
Magnitude of 1?
Yes, a magnitude of 1. There we go. Okay?
Okay.
A magnitude. See, it's not that terrible.
Well, I didn't know that was like the defining factor of a unit circle, but it had a radius of 1.
Oh, yeah. Yeah.
I didn't know that.
Okay. So, unit vector has a magnitude, that's the definition, a magnitude of 1. All right? Now, is the magnitude of v equal to 1? Let's see. What's the magnitude of v? Square root of 8 squared plus a negative 15 squared. 64 plus 225. So that's 289. And that actually is a perfect square. It comes out to 17.
But it's not 1.
It's not 1. So this is not a unit vector, okay? Now think about what we just did with magnitudes. How could I get a vector that didn't change the direction at all, but had a magnitude of 1?
Divided by the same.
Okay, keep going. Divide by...
I don't know what the number.
Well, we want the magnitude to equal 1, and right now it equals 17. So what should we divide by?
17.
Yeah, okay. Now, this is a technicality, but it is important. There's technically no division with vectors. But what you would do is you would do 1 over 17 times vector v. Okay? If I do 1/17 times vector v, that's going to give me this vector 8/17, negative 15/17. Okay?
Okay.
So, basically, here's the idea. That 17 was the magnitude of v. If I take any vector and I multiply it by 1 over its own magnitude, the result will have a magnitude equal to 1. All right, that's what we just did. We took the vector, we found its magnitude was 17, we multiplied by 1 over 17, so the result will have a magnitude of 1. Okay, and that goes right back to what we said. If you do a multiple of a vector, it's going to multiply the magnitude by the same number. Okay?
Doesn't matter if it's in a square root, you still put it under.
Yeah, you can.
Okay.
It'd be nice to rationalize, but it still works. Okay? Now, here's the question. Why would we want to do this? Why would we want to do this?
Makes your life easier.
Okay.
Honestly, I don't know.
What if we wanted this same direction, but we wanted its magnitude to be, say, 60? Okay? But its magnitude was 17.
You make it whatever you want.
Sorry. Well, if we make the magnitude equal 1 first, what could we then do with that vector? If we want the magnitude to be something else.
You multiply it.
Yeah.
To be that.
Multiply it. So if we want this direction but with a magnitude of 60, I could just take this and I could do 60 times 8/17 negative 15/17.
Could you also just figure out that it equals 17 and then divide 60 by 17 and then do it by that?
You can, and that basically is doing it all in one step. You multiply, in the end, what you would do is you do the vector times the magnitude you want. I'll do magnitude you want over whatever the magnitude of v is. Okay? And that will give you a new vector that has that magnitude that you want. All right, so yeah, that's great that you put that together. We just did it in two separate steps. We found the unit vector first, then we made it have a magnitude of 60. Okay?
So you just divide 60 by 17?
Yeah, and now that we're doing that multiplication, whatever that is, okay, that would be 480 over 17. And a negative, let's see, 600, negative 900.
Wait, why would we do this if we want?
Because this vector right here, now if I did my magnitude formula, this vector right here has a magnitude of 60. Okay?
What if we want to take the magnitude?
Yeah. Okay? And you guys can see, you can make the magnitude equal whatever you want. So